When we talk about catastrophic failure, it's not always a rupture. Sometimes it's a sudden, silent collapse.
Right. In tension, things rip apart. But in compression, a whole different enemy appears. Instability.
Exactly. Buckling isn't about the material's strength breaking. It's about its entire shape failing.
Just grab a plastic ruler and press its ends together. It bows out, right? That's buckling in action.
And lucky for us, the brilliant Leonhard Euler gave us this formula to predict that critical load.
And believe me, this isn't just theory. We see this threat in all sorts of critical equipment.
So, how do we stop it? Well, we don't guess. We rely on incredibly strict, standardized codes. You've basically got two main philosophies: the European formula-based approach and the American graphical method. Okay, let's dive into the ASME approach. It's a really practical, step-by-step process used all over. It starts with the vessel's pure geometry, its ratios, to find a value they call factor A. And factor A is all about the shape. How long and thin is this cylinder? That's it. Then you use factor A to find factor B, which finally brings in the material's properties.
Once you have factor B, you just plug it into this simple formula to find your safe pressure.
Let's run a quick example. Here's a pretty typical carbon steel tank that's under full vacuum.
We just follow the procedure. We calculate the ratios, find A on the chart, then find B.
And the answer is 1.6 bar. That's safely above the 1 bar load from a full vacuum.
But here is the massive catch. That calculation assumes a geometrically perfect vessel. Reality is messy. In the real world, tiny imperfections, like ovality or corrosion, can absolutely destroy your safety margin. So, you see, the big takeaway is that manufacturing precision is just as critical as material strength.
Which leaves us with a tough question. Is your equipment's shape really as safe today as it was new?